Notice that there are about 10 students attending. This lecture number, whatever it is. Let's look at last times. We talked about proper maps. We said what is the compactification of a Hausdorff space. We gave definitions. We looked at examples. Then we talked of locally compact Hausdorff spaces. We gave definitions, examples. Here was the definition of locally compact space. We asked you whether C01 is locally compact, and then we made this bounded sequence, which was not convergent. That is enough to show it's not locally compact, because if it was locally compact, there would be a ball. And then by translating it, there will be a ball around the origin whose closure is compact. And then I can put a certain scalar here and make this as small as to fit in that ball, and this doesn't have convergent subsequence. Then we define the proper map. Map is proper if for every z, the product x cross z to y cross z is a closed map. So by taking z to be a point, we saw that every proper map is closed. But the converse was not true. We took the space R to a point, and then this was hyperbola, it was closed, its image was not closed. Is the composite of two proper maps proper? Yes, it is. Here was the. Is a closed embedding proper? The answer is yes. You are asked to show it. If y to z is proper and z is a space of y, is this map from inverse image of z to z, is that map proper? And the answer is yes. Again, you are asked to prove it, or perhaps I told you the argument. Then we proved here that if x admits a compactification x prime, and if x to point is proper, then x is compact. That was through looking at its diagonal, which was closed, and therefore its image was closed, and closed inside something compact was compact. The statement was if x is compact and y admits a compactification, then x cross y to y is a closed map. And that proof was given here. We took some compactification y prime and put this inside, and then its inverse image was this. And this map is closed because this is compact. X is compact, and so on. So, okay. Then we started talking about one-point compactifications. We looked at examples. For an empty space, the compactification is a single point. If x is a single point, then compactification are 2 points. 1-point compactification. This is that extra point. Usually the extra point is called infinity. You will see the reason soon. And if x is the open interval, then the 1-point compactification is a circle with that extra point here. Okay, then here was the general construction of a 1-point compactification. How you take compact subsets and take its complements to be the basic neighborhoods of the point at infinity. And now take the topology generated by this basis. In particular, if x itself is compact, then one of these compact sets you can take x itself. Therefore, the complement of x, which means that point at infinity, will be open. So that's going to happen exactly when x itself is compact. Otherwise, x is going to be dense in x star. So then we ended with this, that x is compact as well, locally compact, then this is an open embedding. So let's begin by proving this. Okay. So I want to prove that x star is compact, Hausdorff, and locally compact, and this is an open embedding. Let's prove that. So why is One by one, we'll prove the points. Why is X star compact? So let's take an open cover. That means that the point at infinity, this extra point that we are talking about, star, let's say it belongs to U0. Let some open neighborhood. Okay. But what are basic open neighborhoods here? So basic open neighborhoods of that point star are complements of compact sets. Therefore, there is some compact set. There exists compact C inside X such that the complement of C, X minus C, okay, is contained in X minus U. I think I should draw a picture to make it clear. So here is X, and I have the point at infinity, and its neighborhoods so there will be some compact set C. This is how C looks. And then that is the kind of basic neighborhood. So U must be something inside C. This U must be inside here. Okay. Now, so okay. No, I shouldn't say U must be inside here. What have I written? So this is X minus U. Okay. I think I am getting the containment relationships probably wrong. Okay. So there is some C and X minus C union star is a basic open neighborhood of star. So X minus C union star is contained in this U. Whatever that U is. So U must look something like this. I'll draw a picture of U. Let me draw it in a different color. This is how U will look. U is this orange set. It's a neighborhood of infinity. And X minus C is this remaining stuff, and star is contained in U. Star X minus C. And this means, because since the union of all UI, union of the UI is all of X star. So one of them, that one I have called U0. So one of them is this U0 that covers rest of it. So there must be lots of others which cover the remaining. Okay. Now, because this C is compact, okay, there will exist some finitely many U0, U1, U0 I already have, U1, blah, 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 UN. that cover C. And together, since I have already included U0, that means, so these cover X star. Because the complement of this closed set I have already covered by this U0. And so now rest of it is covered by something finitely many. Together they cover X star. So for given any open cover, I have found a finite subcover. So the first point is this is compact. So that is done. Why is it Hausdorff? Yeah, can anybody tell? So if I have 2 points, see, first of all, X is open. X is open in X star because we have declared the basic open sets to be open sets in X and complements of compact sets. So this is a basic open set, it's open. So because this is open and if I have 2 points inside X, I have disjoint neighborhoods within X of those 2 points, showing that X star is Hausdorff. So now we know that X star is Hausdorff, X is open. What are the different points we have to show? Compact, Hausdorff. Now we want open, okay, these 3 points we have shown. Now we want to show locally compact. That local compactness, if you remember the picture, looked like this. That given a point and given a neighborhood, there is a compact set inside which there is a neighborhood. We want to show that. So we already know this if the point is in X, because we are given that X is locally compact. The only question is why is this true if that point is the point at infinity? Okay. So a point at infinity, why does every neighborhood contain a compact neighborhood? Yeah. So let's take a neighborhood of the point at infinity. I'll need some extra space. So let me create some space. Okay, where are we? So local compactness. At this is what we want to show. So take a neighborhood. Let X minus C union star be an open neighborhood of star. Inside this, I want to produce a compact set inside which there is an open neighborhood. So how do I do that? So each point of C has an open neighborhood inside which, so given, okay, I should say given an open neighborhood of any point of C, for any point of C, okay, and any neighborhood of that point, there exists a compact neighborhood inside. So I'm now going to draw a picture and ask you to write the argument. So here's that C. Okay. And there's that point at infinity. And I want to create a compact set here inside which there is an open set. Okay. So how do I do that? Yeah. So this point and any point of C, because I have shown it is Hausdorff, there's an open neighborhood here and there's an open neighborhood of this, which are disjoint. For each, I have one open neighborhood, one open neighborhood, one open neighborhood, one open neighborhood. And finitely, when you cover this, and so I'll take the intersection of all those open sets and the union of these, and thereby create an open neighborhood of C and an open neighborhood here, which is disjoint from it. But what is an open neighborhood here? Okay. Now, each of the points in this open neighborhood has inside it a compact set. So when I take this open neighborhood, inside this is a compact neighborhood, inside it is an open neighborhood, and I can so demand that the smaller open neighborhoods cover C. Then the union of these finitely many compact sets is a larger compact set. So there is a larger compact set which has C inside it, and its complement is an open neighborhood. Okay. So, okay, some point I'm missing. So I'll leave this proof at this point and I will return to it later. Meanwhile, let me leave it to you as an exercise. This little point I'm missing, I think. Okay. Now, let's come to the next point. If X is compact, then X to Y is proper. I want to prove this. The idea is this. You have any map from X to Y, you have any arrow in any category with products, I can factorize it like this. I can go from X to X cross Y, and from there I can go to Y in 2 steps. This is the graph map. This sends X to X, X. This is the projection map which sends X comma Y to Y. Okay. Now this map is a closed embedding. This is a closed embedding because all these spaces are Hausdorff and the map is continuous. So this is a closed embedding. So in pictorial terms, this is how the graph looks. And from a point X, I'm going to the point on the graph and then taking the projection, and the composite is the map F. So this map being a, and we have already told you that the graph is homeomorphic to this domain because its inverse is given by this projection from the graph. So this is a closed embedding. And this map is proper because X is compact. This is proper because X is compact. So this proves that this is a composite. This is a composite of 2 proper maps. We have earlier proved that any closed embedding is proper, and we have also proved that when X is compact, this projection is proper, and we have proved that composition of 2 proper maps is proper. Closed embeddings are proper is something which we have proved before, or it was left as an exercise to you. In any case, you are to do it. If I am not done it to you, this is easy. This is easy exercise. Okay. Now, next, if X to Y is proper and if Y is compact and X is compact, the reason is this. I take X to Y and I compose it with y2 point. This is proper because y is compact. This is given to be proper. And therefore, this is a composite of two proper maps. So therefore, this is proper. And therefore, X is compact. So we have proved this. Next point. If X to Y is proper, then the inverse image of any compact set is compact. Why is that so? So here is X, here is Y, here is F. Here is something compact, okay? And here I'll take F inverse C. Now, because F is proper, this is proper. This is one of the statements proved in one of the earlier lectures. So this is proper, and C is compact. So from C to a point, it is proper. Therefore, F inverse C to C is proper, C to point is proper, therefore this is proper. This is proper. Therefore, F inverse C is compact. Now next statement. If X and Y are locally compact, an inverse image of any compact set is compact, then F belongs to a unique continuous map from X to X 1 point compactification to Y 1 point compactification, mapping star to star. Proof. So because an inverse image of any compact subset of Y is compact in X, and those are, so if I take, so take a basic open neighborhood, let C, Y be compact. So I'm going to call this map F star. Okay. So what is F star inverse of Y minus C union that extra point of Y? What is it? This is equal to X minus F inverse C union the extra point of X. Okay. So this was a basic open set, and its inverse image is this open set here. Therefore, this map prolongation is continuous. For any other point which is already in Y, the inverse take a tiny neighborhood within Y, and then its inverse image is what it is already, and that is open, and this is open. And so we have shown that this prolongation, which sends star to star, is continuous. Now, let's come to the next point. If X and Y are locally compact, and if X to Y is, then X to Y is proper if and only if the inverse image of each compact subset is compact. So this gives us a usable criterion to decide something is compact, like the Ein-Borel theorem. And we have now essentially proved it. Because if something is proper, then of course the inverse image of compact set is compact. That we know, that we have proved in any case, that if something is proper, then the inverse image of any compact set is compact. Now we are saying if the inverse image of each compact set is compact, then the map is proper, and we are saying it under the circumstances of X and Y are locally compact out of proper. So how do you do it? So because inverse image of each compact set is compact, this has this prolongation, F star. Let me write it vertically. So therefore, there is X star to F star going to Y star. I have this unique prolongation, and these are compact. This is proper. Okay. And now there is Y, and its inverse image is X. And this map is F, therefore F is proper. Now for a map from R to Rm to Rn, let's take two Euclidean spaces. The following three things are equivalent. F is proper, inverse image of each bounded set is bounded, and limit as norm of X tends to infinity of norm of Fx is also infinity. Proof. So if F is proper, inverse image of each compact set is compact, and therefore inverse image of each bounded set is bounded. Because you know that in Rn the compact sets are the closed and bounded sets. To go from B to A, if the inverse image of each bounded set is bounded, you also know that inverse image of each closed set is closed because F is continuous, and therefore the inverse image of each closed and bounded subset is closed and bounded, and therefore F is proper. Inverse image of each compact set is compact. Now C is exactly one way of saying that inverse image of each bounded subset is bounded. This B is obviously equivalent to C, and so all three are equivalent. Now let Fz be a complex non-constant polynomial. Then I am saying that this map is proper. Okay. So what is limit as z tends to infinity of Fz? Once it is not constant, then that is infinity as F is a non-constant polynomial. And therefore it is proper by this. Now my question to you. I have Rm to Rn a linear map. Spelling mistake. I have a linear map. Is this map open? Is a linear map open? When is it open? Pawan, is anybody there?
Yes, sir.
Should we close the lecture, Pawan?
Sir, if F is injective, then
Somebody willing to answer? Yeah, you are. Who is answering loudly, please?
yes, sir. Is F injective, then is it open?
So that's a good answer. You are saying that what if f is injective? So let me take R1 to R2, x-axis, x-axis. Is this injective? Yes, what do you think?
Yes, sir.
Is it open?
No, sir.
No. Okay. You want to change your answer? Your attempt was not bad. Only change, make the obvious change. Instead of injective, about surjective.
Yes.
Yeah?
Yeah.
When is f open? The answer is if and only if f is surjective. Okay? You guys prove it as an exercise. When is f closed? Anybody willing to answer? Yeah? Somebody willing to answer? Why don't you try with R1, R2, R3, R0? That when is a linear map closed?
So the above you gave R1 to R2. So
Yeah.
if I have a map from R1 to R2, then it is closed.
Correct. Very good. So can you guess what is the general answer? When is a map closed?
Yeah,
Linear map?
the guess was that F must be injected.
Correct. So as Roshni says, but this again doesn't look right. I'll say it like this. There is one map which is always a closed map. Okay, with one exception.
Trivial map.
Take Rm to 0. Okay, this is a zero-dimensional vector space, R0. This is closed. Okay. Otherwise, you will have to think of injective maps. These are the two possibilities. Is closed. Again, proof. This is simple combination of, and this is just very elementary topology, yeah, and linear algebra if you want. Okay. When is F proper? Any guesses? When is F proper? Any guess when F is proper?
Sir, proper maps are closed.
Yes, indeed, they are closed.
So the F must be injective and
Yes, yes, must be injective. But is every injective map proper? Yes, it is. So this is the, you have to check, because that answer is already given to you here. But this is not proper. Only this. This is not proper if m is greater than equal to 1. Okay. This is close, but not proper if n is equal to 1. You see, this was a very simple exercise that tell when Rm to Rm is open, close, proper. Whenever you are given any new definitions, you have to check them with examples that you know, and you know your linear algebra. Why don't you combine the topology that you are being taught with the linear algebra that you know and see what it gives? Now I'm going to tell you something called inverse function theorem, which is openness criterion. Okay. So the more general openness criterion. So I am now going to talk of Rn and Rm, and the map need not be defined from all of Rn. There is some open subset here, and on which there is a map F. F is a continuously differentiable map. Okay. And X is a point of view. Then we can approximate F by a linear map, and that linear map is called the Jacobian matrix. F1 by D, X1, blah, 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 blah. N. df m by dx1 blah 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 dfm by dxn. Take this matrix. Let me call the point P because there are too many x's here. This is so, and evaluate this at P. Okay, meaning take the values of all these partial derivatives at the point P. And that is a matrix. This is a certain matrix, which is m by n. This gives a linear map. So if you have studied your calculus of several variables, it will tell you that if rank of A is m, then F is open at P. So rank of A is m means A is surjective. And for a linear map, surjective was the criterion of openness. Remember, we proved that we didn't do. You were asked to prove that a map, linear map is open if and only if it is surjective. And any map can be approximated by a linear map near a point, and so that is surjective. Sorry, that map is open at that point if and only if this Jacobian matrix is surjective, which means its rank is n. So for a 2 by 2 matrix, suppose it was from R2 to R2, this map, maybe even defined everywhere. So you will send some x comma y to, let's say, u comma v. And then you look at this determinant, du by dx, du by dy, dv by dx, and dv by dy. And you will demand that the rank of this is 2, should have rank 2. Which means the determinant of this at that point P should be non-zero. And then it is open there. Yeah, understood? Very good. All right. So with this, I'll give you Narasimhan's proof that the field of complex numbers is algebraically closed. It's a very simple proof based on inverse function theorem. The proof goes like this. So I take some non-constant polynomial a non-constant polynomial. And what I'll prove is that if we will show that the map, corresponding map, f from C to C is surjective. This is what it means to prove that something is algebraically closed, because then it will take the value 0. Same as saying that it takes every possible value, because fz minus a 0 of fz minus a is some value of z where fz becomes a. So taking the value 0, taking all values, same statement. So if I show that it takes all values, it takes the values here. And if every polynomial takes the value 0, then replace that polynomial by f minus a to show that it takes the value a. Okay, so I am going to write this fz as f of x plus iy. And its answer is going to be u of xy plus I times vxy. Okay, fz equal to f equal to u plus iv. This is how I have decomposed it into its real part and imaginary part. Now you guys know from what we saw above that this matrix determines whether it is open at a point. I want to take its determinant. So what is this determinant? Du by dx, dv by dy minus du by dy, dv by dx. Okay, can you simplify this expression? Is a polynomial a complex analytic function?
Yes, sir.
Therefore, yeah, you had now a month of complex analysis. So, bolo.
So since function is analytic, so we can write use Cauchy-Riemann equation and write curl u over curl x square minus plus curl u over curl y square.
Very good. So who was answering? What's your name? Who is
So
speaking?
Sonakshi.
Okay. So these are called what equations? So this
Cauchy-Riemann.
Cauchy-Riemann equations. So by Cauchy-Riemann equations, this is indeed this. Du by dx is dv by dy. And du by dy is minus dv by dx. So this whole expression becomes equal to u by dx square plus y plus, because the other Cauchy-Riemann equation had a minus sign in it, plus d u or dy square. And this is equal to f prime z mod f prime z square. Okay. Because you know that f prime is going to be du by dx plus I dv by dx. Yeah, I can take the derivative. So here I change it to dv by dx. dv by dx. Good. This is minus of this. Okay. So I know that f prime at z is du by dx plus I dv by dx. The reason is when I want to take complex differentiation, I will take my h. See, f prime z is equal to f of z plus h minus fz upon h. I can take h to be real, and therefore the expression will turn out to be this. This is mod f prime z square, and so this shows that if f prime at some point p is not equal to 0, then f is open at p. Okay. So now I am going to ask you, how many solutions can this have? Suppose f has degree n, then fz. This is a non-constant polynomial, therefore this degree is greater than or equal to 1. Then what is the degree of f prime? F prime has degree how much?
n minus 1.
Correct. Okay. And can f prime be identically 0? No, because that will mean that f would have been a constant whose degree then would have been 0. So this is a non-constant polynomial. Non-constant polynomial. Right? Therefore, how many roots can f prime z have? We have not proved the fundamental theorem of algebra. We don't know whether it has any roots at all, but you know that a polynomial of degree n has at most n roots. I'm going to say this in this bracket, that a polynomial of degree n has at most n roots. And this is true over any field. It's a simple algebraic fact, because every time there is a root, you can factor out a linear polynomial x minus a, and the degree drops by 1. Okay. So you know reals, a polynomial of degree n has at most n roots. It might not have roots. How do you know it has any roots? But it has at most those many roots. So there is a set. So let A equal to set of all P such that f prime at P equal to 0. This is a finite set. So now I take C to C. I call the coordinate here Z, I call the coordinate here W. And so I have the set A here, and its image is FA. Okay. Now, how large is the set F inverse of FA? I am saturating A. So how many points are here? At most n minus 1 points. Because after all, F may not be injective on that set A. So there are at most n minus 1 points. Okay. A has at most n minus 1 points. And how many points can go to those n minus 1 points? It's back to how many roots can F have. Each one of those points is taken at most n different points here. Okay. So this has at most n into n minus 1 points. So now I take C minus F inverse of FA, and I am mapped to C minus FA. This is the map F. This is open. Okay. Now, as you know, limit as z tends to infinity of fz is infinity. It's a non-constant polynomial. Therefore, F is a proper map. Okay, therefore F is proper. So this map C F C is proper. And if I take this subset here and take its inverse image, that is the inverse image of this set. The inverse image of this set is this. And therefore this, so I'll call this F, well, let me call this open set as U. So this F is restricted to U. So this shows that F restricted to U is proper, therefore closed. So this map is both open and closed. Now the last ingredient, R2 minus any finite set, F. This is a finite set, is connected. So I have this R2 and I remove some finitely many points. It is connected. You can show that it is path connected. Given any 2 points, you can connect them with a path. Here's a point, and you can always avoid these in-between points and join them by a path. So this is connected because it is path connected. Very easy. So the image of this is both open and closed and non-empty, and this is connected. Okay, this is connected, and the image of this is open as well as closed. So its image, and which is non-empty, has to be everything, because otherwise you will have non-empty connected, sorry, non-empty open and closed subset. Complement also non-empty, sorry, the complement will also be open and closed. So the complement will have to be empty, otherwise it will give a disconnection of this. So therefore surjective. So this is surjective. Now this is dense here, and this is a closed map, and its image contains a dense subset. Therefore, F is surjective. Okay. So this is the proof that C is algebraically closed by simply using Cauchy-Riemann equations and the inverse function theorem in 2 variables and the basic technology I have explained to you of proper maps. Okay. So I have a few minutes to go back to the proof I messed up in the beginning. Where was it? Local compactness at infinity. Okay, this is what I want to do. So I'm going to draw a picture and not try to write notation and complements all at the same time, otherwise I may again mess it up. All right. So I'm going to draw my space. Here's my space X. And there's that point at infinity, and I want to show that given any neighborhood of it, inside it is a compact neighborhood. So to give a neighborhood of it amounts to taking a compact set C. And the complement of C, X star minus C, is an open neighborhood of the point infinity. Okay? Star, whatever you call it. And inside that, I want a compact neighborhood. So the way I will manufacture this compact neighborhood is each of these points admits there's a compact set inside which there is a neighborhood. So each one of them has a compact neighborhood. Each point of C has a compact neighborhood. Let me call it each point X, AX. And finitely many of this A1, AN covers C. And so now I take these finitely many neighborhoods which are contain something open. So this the compact neighborhood means here's something, here's an open set. And each of them, okay. And then I have to say, I have to manufacture a compact neighborhood of infinity, which is in the complement of C. Yeah, still I'm missing something. I think I have to give this a miss and try to work it out without simultaneously explaining it to you. So I'll do it. Tomorrow I'll explain it to you. Okay. So I'll end the talk here and ask you if there are any questions.